Okay, let's get started. So last week we talked about Broward diagram. So this is a very important concept in defect chemistry. So a Broward diagram essentially tells us the quantitative relationship between the chemical potential of the some element and also that with the defect concentration. So the example we used last week is to talk about the kind of the random oxide, basically the monoxide. We know that we can have either oxygen vacancies or oxygen potentials. And if you also include the electron defect, essentially you have all kinds of defects. So you have oxygen vacancies, oxygen potentials. So these are ionic defects. Ionic. Okay. So you also have electron and holes. Okay. So these are electronic defects. So essentially, what we solved for last week is basically to know the relationship between the PO2. Essentially, if you change the PO2, you basically change the chemical potential of oxygen, right? So, and we want to find the quantitative correlation from that to the defect concentration, and the defect including both the ionic and electron defects here. These four kind of defects. So conventionally, what we want to plot is essentially the log-log plot. So we use the we plot log defect concentration with log PO2. So this is essentially because what we find is that defect concentration usually have the power law. So basically you have the power law of PO2 and this N is basically power. We find that N will be something like 104 plus 5 104 plus 106, depending on which regime you are at. Of course, the natural solution is basically take the log on both sides, then N becomes the slope in this plot. Okay, so the way to solve this is basically we consider the defect chemical equilibrium. Okay, so basically we consider defect chemical reactions. Okay, so we have different kinds of reactions. So of course the first one is the formation of the Frankel pairs or anti-Frankel pairs. And with that we can write the chemical equilibrium constant. It's basically something like this. Okay. And we know that's only, Kf is only function of temperature, it's not a function of the concentration. We also have the electronic disorders, basically form of the electron and hole pairs, and we use another constant. However, we also need to link the ionic and electronic defects. So we have the formation of oxygen vacancies, but we also need to try to balance with electrons. And of course, when the oxygen leaves the sample, it goes to the gas phase. Okay. So there's also a constant associated with that. And if we neglect the fraction of this one, because usually we treat in the dilute system so that mostly the oxygen still stays in the place. We have only few of them become oxygen vacancies. So this we can write something like this. And we also have the charge neutrality. So which means, so essentially we count all the positive charges that should be equal to all the negative charges, right? So if we count all these negative charges, should be the same as the positive charge. So as you can see, what we want to solve is actually these four unknowns. Okay, so this four defect concentration, and now we have basically 1, 2, 3, 4, four equations. So we essentially can solve it. However, it might be very difficult because we have four equations, so it might be it takes a lot of trouble to solve it. So therefore, we have the simplified version called Brouwer condition. Brouwer condition basically gives you, we pick two majority defects depending on where we are and try to simplify charging the charge. For example, if we say, okay, if the Kf is much larger than Qiyang, so this means that the oxide is wide band gap. So why that is the case? Because we know the KEL is the basic exponential minus KB over EG. Okay. So if EG is large, then the KEL is small. Okay. So if we have this one, then for example, if we have intrinsic region, so we can basically simplify two terms. Okay. So we can basically neglect the concentration of electrons and holes. Okay. So this basically becomes, we have the amount of oxygen vacancies the same as oxygen interstitials. Okay. So basically last week we go through all these three regimes, basically intrinsic and oxygen poor and oxygen rich. Okay. Also this three regime. So the end of day which we have is basically this plot. So here again, so this part is log defect concentration. We have four different kind of defects, and this x-axis is essentially log Q2. So log Q2 essentially is another way to say that we are changing the oxygen chemical potential in the x-axis. And we have three different regimes. So just draw three boxes. So in the middle we have intrinsic regime, where we already know that the amount of the oxygen vacancies should be the same as the amount of oxygen interstitials. Okay, so this is oxygen interstitials. And if you also solve for electron and holes, you will see they have different slopes. Okay, something like this. So basically, this is the hole. Sorry, this is the electron. So this is hole, and we have the slope to be 1/4. Okay. And of course, if we go to oxygen-rich regime, we can imagine that the amount of oxygen interstitials goes up and will be charge balanced by holes, because oxygen interstitials negative has to be charge balanced by positive charged defects. Then the oxygen vacancies basically go here. We solve for the defect chemical equilibrium, and the slope is 1/6. Okay. So the same thing as the oxygen, as the electron here. So this is the electron. So this regime is called oxygen-rich because we are increasing the amount of the oxygen in this case. So if we write something like so in this case, the let's say, so if I write MO 1 plus minus delta, then in this region it should be MO 1 plus delta, because we have oxygen excess. Okay. And we also have oxygen poor regime. For example, here we have oxygen interstitials balanced by electrons. Then oxygen vacancies balanced by electrons. Oxygen interstitials here, and Maybe I'll draw a little bit up. Then we have, this is the host, yeah. Okay. And of course, in this regime, the slope is minus 1/6. Okay. So I won't go through the details in mathematics because they have been covered last week, and also it should be on the slides. So if you are interested in knowing details, you can look into the slides. Is there any questions about the Bower diagram for students who were here last week? No? Okay. So of course, we know that we can put the values into the plot, right? So, for example, we know that in the intrinsic regime, we have the number of number of oxygen vacancies is same as number of oxygen in tissues. And if we plug into this equation, we'll know that this is essentially logarithm square root kf. Okay. So we can also put other networks into the equation. For example, here we have electrons the same as the holes. Then we put into that equation here, we know that this part is logarithm square root KL. KEL, okay. And also it's easy to solve for this point. Okay, so this point, as we talked about last week, is kind of special. Okay. So basically this point is called a stoichiometric. It's called stoichiometric point, where in this point delta is strictly 0. Okay. Because any point you go to that direction, you have MO1 plus delta. Any point you go through this direction, you have MO1 minus delta. Okay. So basically, anywhere left of this line, we have oxygen deficient, and any part to the right of this line, we have oxygen excess. Okay. So basically, you can also define delta is an amount of the oxygen in the tissues minus the amount of oxygen vacancy. Okay. So in this case. So well, we can also solve for this point. So where the point is. This is very important to know where you are. Okay. So how to do that? Essentially, we know that in the intrinsic regime, we have something like this. We have the amount of oxygen in the tissues as the same as the amount of the oxygen vacancies, and the square root kf. Okay. So essentially, we can plug into this equation. Basically, now we have the KO the same as the kf 1/2, then electron square, then Q2 1/2. Okay. Then this one should be essentially you take this all to the other part. KO 1/2, KF 1/4, then Q2 negative 1/4. Okay. So we know that at the stoichiometric point, so we also have the number of electrons the same as number of holes. Okay. So at the stoichiometric point, so basically this thing should be the same as this one. So this then should be square root of KEL. Okay. Right. So then if you have this one as it's the same as this one, you can solve for the PO2 should be take this here, then just get rid of 104, you get KO squared, then KEL minus 1, then KF minus 1. Okay. So basically you can plug in into here, so this part, this point should be less than KO squared KF minus 1, KEL to the power of minus 1. Okay, so as you can imagine, if you change your material system, essentially what you are changing is this constant. Okay, this values that are going to change. Okay, so it's very important to know where you are depending on your material system. Okay, so you will know that once you can measure all these constants. Okay, any questions? No? Okay. So I guess in this lecture, we are going to first discuss the two purposes, I would say, of Bower diagram. So essentially, why we are going through all these troubles to get something like this. So essentially, this is a map for the defect chemistry. Essentially, if you have this, you know where you are, right? If you change your PO2, you know where you are, okay. Of course, imagine that this is a constant temperature. Essentially, if you change the temperature, you get a different Bower diagram. Because you have a different set of the constant, right? Remember, these things, they are a function of temperature, okay. So we're going to consider the two, let's say, usage of Bower diagram. Bower diagrams. Okay, so the first usage is essentially it gives you a way to estimate storage or storage of charge. Or it can be chemical storage of charge. Okay. So what do I mean? So essentially, the way we, so we know that, I think the perfect example is basically consider a battery. Okay. So let's say it's a solid state battery. Okay. So we have electrolyte in the middle, which can basically allow the lithium ion to go through. Okay, so we have lithium metal for the anode, so it's supposed to be a very good battery. Okay, then we have another compound. Let me call it lithium X. Okay, so basically X can be anything, just a kind of random battery. Okay, so then, of course, battery can give you electricity. So the way that battery can give you electricity is essentially you need to shuffle the lithium from anode to the cathode and back forth because it's supposed to be rechargeable, right? So the way to do that, essentially, you are changing the non-stoichiometry. Okay. So essentially, you can write an equation. For example, if I put more lithium into the structure from here, from anode, because it's lithium metal, to the cathode, what I do is basically put lithium into the structure here. Okay. So you can imagine if you use the language of defect chemistry, it will be something like lithium interstitial and also electrons. Okay. So something like this. Of course, you can remove lithium. If you think of, you start with stoichiometric lithium X, right? Then you start to change the stoichiometry. You can either put more lithium into the structure, or you can remove lithium. For example, if you remove lithium, it will be you take out lithium, so essentially you leave with lithium frequencies and poles. Okay. So of course, usually a system can only do one of it. Okay, so of course some system can do both. So let's just keep it simple. Let's just consider this one for a moment. Okay. So we also can consider the other defect chemical reactions. For example, if I say here for the lithium compound, it can have both lithium excess and the lithium deficiency, then essentially if I have positive delta, the amount of delta is basically this one minus what do you think? Okay. Okay, so this is how we store energy into the lithium-containing compound in the battery material. So essentially, we store it in the case of in the form of both the ionic defects and electronic defects. Of course, it's not very popular in the study of lithium battery because people just usually write this as normal lithium ions, but these are really non-stoichiometric, so you can really understand using the defect chemistry language. Okay. So if we apply the same thing to the oxides, we can actually write other two defect chemical reactions. We can consider that we can also have Frankel pairs. Okay. So this is basically the Frankel pairs. And let's call it K lithium. Okay, so it's basically times this one. Okay. And also, since usually the semiconductors, okay, for the cathode materials, you also have the formation of electron hole pairs. So KEL would be electron and holes. Okay. So now it's basically 1-to-1. Sorry, I've got a very important thing. Okay, so essentially we write a lithium here. So essentially, what you decide the chemical reaction is basically the amount of the lithium or the chemical potential of lithium. So here is basically you write the activity of lithium into the equation, right? So essentially, if you change the activity of lithium, you change the concentration of this defects in these compounds. Okay, right. Of course, you have the charge neutrality. All the positive defect should be, have the same charge as the negative defect. So again, we have 4 kind of unknowns, right? So we have the amount of all these ionic defects, the amount of the electron defects. So they are all always controlled by the activity of lithium. Okay. So what we can do is we can actually draw the Broadway diagram of the lithium-containing compound. So essentially, we can basically simplify the charge neutrality conditions. Again, so we're going to go through this same thing again, just as a practice. Okay. So another thing we want to change a little bit here is that in the oxide system, we assume that the Kf is much larger than the Kel, which kind of makes sense because most oxide has very large band gap. But for lithium containing compound, for example, lithium cobalt oxide or lithium iron phosphate, if you want to use it as the cathode material, it has to conduct some kind of electricity, right? So in this case, we actually assume KEL is actually larger than the KF. In other words, EG is small. So basically, it's still a semiconductor, but the band gap is kind of smaller, right? Remember, the KEL is directly linked to the band gap of the compound. Okay. So then we can say if we have intrinsic regime, if we have intrinsic regime, in this case, since KEL is much larger than KF, then the actual electron and the holes, they are actually the majority carriers. So then we have number of electrons should be the same as number of holes should be square root KEL. Okay. Then the amount of the lithium containing defect is basically linked to this equation here. So we have the K lithium should be, let's say, the lithium interstitials times KEL times A lithium minus 1. So what we can see is that lithium interstitials is proportional to the activity of lithium. Okay. So essentially, we can draw the Broward diagram. So in this case, the axis is not a pressure anymore. So it's basically the log activity of lithium. Okay. So again, this is an intrinsic regime. So we have electrons the same as the holes, and we have the, let's see, so the lithium interstitials, so this is the lithium vacancies. Okay. I'll also solve for lithium rich. So lithium rich, the two majority defects, they are these two. Okay. Because you have more lithium than needed. So you have the amount of lithium interstitial the same as the electrons. Okay, so then basically the whole is KEL over the amount of this one. Sorry, let me solve for these two first. Okay, the K lithium basically interstitials times electrons times A lithium minus 1. We know these two they are the same. Right, so I can write as the amount of this square. Okay. So all we need to know is basically the n, basically the power law n here. So we can already see that in this case, it's proportional to, sorry, not Q, A lithium, 1/2. Okay. So we can also solve for, so the electron is the same as this one. Okay, you can also solve for the vacancies from the Franco pair over there. We know that should be minus 1/2 because this times this should be a constant, right? And holes is also 1/2, minus 1/2, because electron times holes should be a constant. Okay. So we can also put it into this Broward diagram. Okay, so basically now it's 1/2, and this is 1. So this we have these interstitials, the same as electrons, and the holes should be this one. Then the so this is vacancy. Okay. For the lithium, so this is lithium rich. For the lithium pool, I'm not going to write it anymore because we know from symmetry that this basically flips, right? So basically, you draw a line at the stoichiometric point. You just put this here, then you have mirror image. You can get what you have for the lithium pool. Okay. For the lithium pool, you can just draw it. So again, there should be minus 1/2. Okay. So in this case, we have oxygen. Lithium we can see the same as holes. And then you have, so this is the electrons, right? In this case, this is the lithium in the tissues. Okay. So this is basically a Brouwer diagram. It's a Brouwer diagram for lithium containing compounds. Okay. With non-stoichiometry. Okay. So which means the lithium concentration can change. However, in any storage in a battery, this is kind of we are not quite used to that. Okay. What we are used to is basically plot something like this. So if we want to plot it, it's basically the voltage. Essentially, if I use the letter E here, so basically the voltage of the battery, all the potential, the electrical potential of your cathode materials. Okay. So I think after the next lecture, so you're going to learn that the voltage is essentially determined by the chemical potential of lithium. Okay, so of course it should be formally the chemical potential of lithium should be the voltage for such a battery should be the chemical lithium for the lithium electrode for this one minus the chemical potential for the for this one. Okay. Of course, I need to divide it by Faraday constant. We're going to talk about this, I think, end of next lecture. But I'm going to use it first. Okay. However, what you can see here. So because I assume that we are using the lithium metal as the anode, the chemical potential for any pure materials should be 0. Okay. So this will be 0 eV or 0 kilojoule per mole. So or it doesn't really change, right? Because it's metal. You put a more lithium into the metal, or you take lithium away from the metal. It doesn't really change the chemical potential of it. Okay. However, this thing actually changes. Okay. Depending on the concentration of the lithium in the sample. Okay. So as you can see, that the voltage is really determined by the chemical potential of this one. Okay. So if I write minus E, so it's basically the chemical potential of lithium. Okay. We know that the chemical potential of lithium should be some kind of the standard condition than RT logarithm log A lithium. Okay. So I can also write. So this thing is based 2.303 RT logarithm. I mean, with 10 as a base, anything. Okay. So what you can see from here in the Brouwer diagram, so the x-axis is basically logarithm activity of lithium, right? So it's nothing but the potential or the voltage if you are going to change for the x-axis. So in other words, essentially what we are drawing here is Brouwer diagram, right? Brouwer diagram means that we are changing the chemical potential or activity of lithium. Essentially what we are doing is changing the voltage of such a cell like that. Okay, so this is the x-axis. So what about y-axis? So we know that what we want is basically some kind of capacity or storage, the charge, right? So the charge is basically determined by delta. And we know that delta is the amount of the lithium excess minus the amount of the lithium efficiency. So this is the case for this one. Of course, if you flip it, you're going to also flip delta. Okay. So basically here the charge. Basically what you can store is you are changing the Austin stoichiometry. Okay. Right. So let's say the Q, if I just replace with the delta, as in within 1 plus delta. If I just define like this, so what you're going to see is that in the intrinsic regime, the delta is very small. Why? Because you can see this is logarithm. So again, it's a log defect concentration. Okay, so this log defect concentration, so here it should be very small. Okay, because it can be 10 to the minus 1, can be 10 to the minus 3. So these two are very small. So again, so in this case, you can see that the y-axis is not logarithm anymore. It's basically linear. So what you're going to do is basically convert the y-axis here from the logarithm to just linear scale. Okay, for the intrinsic, essentially you have no complexity at all. Okay. So what about lithium enriched? Then if you go to lithium enriched, you really have storage. Okay. So you can see that in the lithium enriched regime, delta will be something like this. And you can safely neglect this one because this will be automatically lower than this one. So it will be roughly the same as this one. We know that it has power law of 1/4. It should be some kind of constant, then times a lithium and 1/2. Okay. However, we know that we want to get the axis as a logarithm. We don't want to have the axis as the activity. Right? We can write something very awkwardly. So it should be some kind of constant. Then it should be exponential. Logarithm should be log a lithium, then 1/2. Okay. So anyway, what I'm getting is doesn't matter what's inside. After all, you have the exponential. Okay. So it will be somehow exponential with the axis. It'll be taking off. Okay. You can kind of see that because if you have exponential here, you take logarithm for the y-axis, you get a linear scale. Okay. So we can do the same thing for the other part for the lithium pool regime. For the lithium pool regime, if I keep using this definition here, so if I do not put a plus minus sign here, if it's just plus, then this should be negative. Okay, for the delta. If I define delta like this. Right, because we have much more lithium vacancies than lithium interstitials, right? So it should be pretty much here. Okay. So again, this is kind of symmetric, so it'd be something like this. Okay. So let me be less dramatic. Okay. So essentially, what you can convert from the Brauer diagram to any storage is basically you have something like this. Okay. So it kind of makes sense because sometimes you do see battery doing something like this. However, 99% of case you don't see something like this. Okay. Why is that case? The reason why is that there's a very important assumption when we already write these equations. Okay, so when we start to write these three equations, so there's an assumption we already made, which is we assume dilute system. Always dilute limit, which means no interaction. No between defects. So what does that mean? So basically, you need to know where you have this equations, okay. So this equation formally should write something like this. For example, the Kf should be writing like the activity of the defects over the standard condition, okay. Again, it should be activity of leaking vacancies over the activity of standard condition, okay. Something like this, okay. But we just replace it with the fraction, the molar fraction, or there's some kind of concentration. So the assumption we make is basically any defect will be the same as the concentration. Of course, formally you write with activity coefficient, or we say this coefficient should be 1. Okay. So this is generally true when you have this much smaller than, so basically we have very dilute system. So imagine that you have a bunch of defects. For example, you can have vacancy here, an electron here, and a hole here, whatever. Of course, this might not be something like this, but you can imagine, okay. So if you just have a few of them, I mean, they are kind of, there's no interaction, or you can have another same defect, another vacancy here. However, if they are getting closer, which means you have more and more concentration, they start to have interactions. Okay. So you can imagine that the easiest way to imagine is that, okay, so this is negative charge, this is negative charge. If you put two things closer together, you start to have the Coulombic interaction, right? So basically, you have to think about the electrostatic interaction between the defects. Or if you have negative charge defects and positive charge defects, they start to attract each other. So this kind of interaction makes this definitely equal to 1. Okay, so when you screw up with every equation, you write it here. Okay, so which means you cannot use Brouwer diagram anymore. So which means Brouwer diagram only applies when you have dilute system. So for oxides, most cases, the concentration of defects are small. However, when we know that for this lithium containing compound, for example, if you have lithium top oxide, the delta can be as large as 0.5. Okay. So this by no means a dilute system anymore. So then you cannot use all this equation, and Brouwer diagram basically fails. You don't have this kind of nice poly anymore. Okay. You can still think of in the defect language, but it's just like you don't have the kind of nice polar anymore. Okay. So since it will be much more complicated. Okay. All right. So this is basically how we do storage using the Brouwer diagram. For something like metal oxide, so since you also have the non-stoichiometry in oxygen, you can also store charge by changing the oxygen stoichiometry. However, just nobody will use oxygen to make a battery because it's limited use, right? You always want something like lithium or sodium, or something like that. Okay, so we already talked about the first usage of the Brouwer diagram, which is give you a defect chemical explanation of charge storage in energy materials. So the second usage is basically to understand the conductivity. Okay. Of course, conductivity has two aspects, both the electronic conductivity and ionic conductivity. Okay. All right. So first, so what we study, for the most of cases, they are mixed conductors. So these are mixed ionic and electronic conductors. or it's called MIEC. Okay. So then we essentially have two different conductivity. We either have ionic conductivity and also electronic conductivity. Okay. So basically, usually people use the notation sigma ions and sigma electrons, something like this. So first of all, the conductivity. We're actually going to spend a lot of time talk about these two things later in this lecture. So we'll understand that it might not be easy to really know or separate the ionic and electronic conductivity. So they are going to give you a lot of trouble. But here, so we all know that from high school physics to measure conductivity, you essentially have a piece of sample with the, let's say, the area of the A, and then the length L, right? So then they basically have the resistance is proportional to L, and inversely proportional to A, then with rho, or rho is resistivity, or can be 1 over conductivity. So if you can accurately measure R, the resistance, so then you can quantify the conductivity, which is the material's property, right? Okay, this is a macroscopic picture. We all know, however, that in macroscopically, for ions, in this kind of ionic crystals, the conductivity is actually contributed by defects. For example, the way that you can have the oxygen ion conductivity is because you have oxygen defects or oxygen vacancy on your tissues. And for electron, you can have both electrons and holes to conduct. But anyway, for any conductivity, we have the microscopic picture to know what kind of terms goes into this. You should be, I think you have learned that in your high school physics or undergrad physics. It has three terms. Okay. So the N is basically here is the number of charge carriers. Can be electrons, holes, or for example, oxygen vacancies, oxygen tissues, depending on what kind of sensor you have. Then E is basic charge. This is not M, so this is a big mu. Okay, it's grey letter mu because usually when we write mu, small mu, so that's reserved for chemical potential. Right, so I have no other way to use number mu, so I basically write a big mu. Okay, so that's great letter mu. So this is basically mobility. Basically, the quantification of how fast this charge carrier can move, right? So next lecture we are going to talk more on the mobility and its relation with diffusivity. But anyway, for now, we just assume, okay, this is another parameters that are going to determine the conductivity. It kind of makes sense, right? So basically, the amount of the more charge carriers you have, the higher the conductivity is, or the same number of charge carriers but can move faster, then you also have higher conductivity. Okay. Then we also sometimes it's convenient to write because there's a number of charge carriers. That's in basically the number per unit volume, for example, per centimeter cube. Okay, so basically the number of charge carriers. We also want to use a concentration. Concentration we know is molar per volume, something like this, right? Of course, if you want to convert from this one, from number to concentration per mole, you have the Avogadro constant. And the mu here, okay. And then you have something in the middle, basically, so this is 1.6 times 10 minus 9 coulomb, right? So this is the 6.2 times 10 minus 3 per mole. Okay. So the product of this is basically the Faraday constant. So the Faraday constant that is constant, which is 96500 coulomb per mole. Okay. Right, so, or if I clean up the mass, basically C, F, M, okay. However, so this is usually for electrons. For ions, there's another complication, is that ions can have multiple charges. Okay. Or you can take the absolute value. For example, for this and for oxygen vacancy, or this one, Z should be 2, because every charge carrier gave you 2, right? So also write the Z here, or the absolute value, I mean, depending on what you want, okay? So basically, this is the, so this equation is usually what we want, okay? For example, the ionic conductivity should be C ion, then D ion, F mu ion, okay? So this is the ionic conductivity. For the electronic conductivity of semiconductors, because most of these mixed conductors, they are semiconductors, right? So you have to consider both electrons and holes, or what usually people write is N-type and P-type. Okay. You may have more electrons than holes, or more holes than electrons, but in the formal treatment, you have to sum these two. Okay, then you have, for example, Cn, which is the concentration of electrons. Here, for the electron hole, they have only one charge. So Z is 1. Cf mu n plus Cp F mu p. So this is basically the expression for electrons and ions. Okay. So what you can see from these equations is that the conductivities are really connected with the concentrations. So if we assume that the mobility is constant, right? So if the mobility are constant, then if you change the concentration of the defects or change the concentration of electron on the holes, you're going to change your conductivity. Okay. So here's why the Brownian diagram is very important, because it tells you how the conductivity is going to change as function of external driving force. For example, if you change the PO2, how does the electron and the ions contribute conductivity change, right? So this is a question we want to understand using Brownian diagram. Okay, so example we're going to talk about is something quite prototypical. It's strontium titanate. Okay, so for those who are not familiar with this one, it's actually a perovskite oxide. Carriage oxide. So if you draw the kind of structure, okay, so it has the titanium in the middle and strontium at the corner, okay. So these are strontium. Then the oxygen is actually at the trace center, so forming this kind of octahedra. So this one here. Okay. So essentially a cubic structure. Okay, with strontium at the corner, the titanium sits in the middle. By the way, quick quiz. So what kind of crystal structure of this one? Is face-centered cubic or something like that? I mean, it's a cubic structure, right? We know that for cubic structure, we have body-centered cubic, face-centered cubic, simple cubic. So which one is this? Okay, that's a very typical wrong answer. So it should be simple cubic. Okay. Okay, so the reason is that this is TiO3, right? So of course all the oxygen takes at the face center. However, face center means that if you move this one to this place, everything else should actually overlap. Okay. So if I say, okay, if I take this out and say, okay, everything is upstream. That's phase center qubit. However, remember that at the corner I have strontium, here I have titanium. So the only way that the unit cell can repeat itself is that I remove the whole unit cell. Okay. Anyway, so this is the. Anyway, it has nothing to do with this class, anyways. Okay. Anyway, what we want to study is this thing at high temperature. High temperature, what kind of ionic connectivity and electronic connectivity can contribute. Okay. So, however, we need to know what kind of the defects we are dealing with. We are, of course, dealing with electron and holes. And so this structure, because it's cubic structure, is pretty packed, right? So it cannot really have oxygen intertissues, right? Otherwise, and there's just not enough room for oxygen intertissues. But it can form oxygen vacancies. However, there's another usual defect, very common defect in this structure, which are not really covered by what we talked in the beginning, which are extrinsic defects. So this is kind of like dopant we introduced in the silicon. For example, silicon we have donor dopant and acceptor dopant. So in this strontium titanate, if you buy this in single crystal, it's already doped very likely with kind of impurities. Okay, most commonly you have something like iron. So basically, when you make these crystals, there will be some impurity that goes into the structure. Most commonly iron, aluminum, or magnesium. Let's, for example, think for a moment, assume that as iron in the structure, the iron is usually taking up the titanium site. And iron in this structure, anyway, let's say it's aluminum, because iron is complicated. Let's say it's aluminum. Okay, aluminum is 3+, titanium is 4+, right? So it has one negative charge. If you have aluminum as impurity, okay. So this is basically impurity. You can also call it dopants. Whether you like it or not, you have this in your structure. So we know that in the if we dope the system with this negative charge defect, there has to be something positive to charge balancing, right? It turns out that when charge balancing, we have oxygen vacancy. Okay. So of course, to have the charge neutrality, it has to 2 to 1 for the stoichiometry. Again, so what we can think of is that we can think of a bunch of the defect configuration, but first let's think of the charge neutrality conditions. All the negative charge defects, aluminum, two. So in this system, the band gap is very large, which means that we can safely ignore these two. And all we need to think of is basically this one. Okay. This is the boundary condition. So this is the boundary condition. Okay, so we have 3 different unknowns, right? So we can have we have 1, 2, 3. So we have to solve for that. We don't have oxygen intertissues because I told you that that's not important. So this thing we know that for sure because we kind of know once we make the single crystal, we kind of know we can do ICP or whatever to know the concentration of this thing. It's usually in the ppm level. Depending on how pure the single crystal is. Okay. So of course we have the electron and hole. We have the electron hole pairs. That's of course in this case That's, again, I remind you, that's exponential kBt Eg. Okay, so no problem with that, right? So we need one more equation. One more equation is basically this one. We can still have the gas exchange. 2E. Okay. We can still have the gas exchange. And then we have oxygen vacancy concentrating times electron squared Q2 1/2 to be KO, So we know from this Boundary condition that for most of cases, oxygen vacancy concentration is fixed by this one, right? So this one is basically 1/2 of the dopant or impurity concentration. And from this one, so this is a constant. Okay, so then you can see from this equation, the electron basically proportional to minus 1/4, right? And the holes we know should be proportional to 1/4. Okay, no problem with that, right? So it's kind of like an intrinsic regime we saw before. However, in this case, it's actually extrinsic dopants which fix the concentration of the ionic defect. Okay, so we just draw the Boundary diagram. We only have just one regime for this one, so it's kind of easier than what we solved before. Okay. Again, what we have is log CO2 here, and the log defect concentration. Okay. So as I was telling you that the amount of oxygen vacancy is kind of fixed by the amount of the dopant concentration or impurity concentration, right? Then we have the so this should be a hole. It should be electron, and it should be 1/4. Okay. Right. No problem with that. Any questions? No? Okay. So, however, we don't really want this one. So this is not our end result. End result is to understand the conductivity. Okay. So what we want to know actually is convert this, just like what we did last class to convert this, convert the Boundary diagram to the charge storage. Here we want to know the conductivity or log conductivity. I mean, it's the same thing, right? As function of the driving force, basically log CO2. So if you think about experimentally, what you take is you take a particular sample and you control the CO2, then you measure the conductivity, and you basically construct such a plot. Okay, so how we approach this question? So this is basically tells you the concentration. Okay, the concentration I just erased. Anyways, is basically this one, right? So our assumption is mu is constant for everything. Okay. So we have three different conductivity. We have conductivity of oxygen vacancies, right? So basically, the amount of what I'm going to write, basically just write something like this. The amount of oxygen vacancies. If I do something like that, usually you have to be a little bit careful because so this is defined as molar fraction. Okay. So for a lot of the which we use is basically 1 mole of strontium titanate. Of course, this thing doesn't exist. Let's say this is a molecule. How many more of oxygen vacancy you have? Okay. So you have to time this as the concentration of strontium titanate. Okay. So how do you do that? You basically say, okay, so you basically say, okay, you know the unit cell, okay, unit cell. You can, do X-ray diffraction or whatever. You know the volume of a unit cell. For unit cell, you have one this thing. Okay, right. So this is basically a number of this thing here, right? Also, concentration is basically the number of Avogadro constant. So this is how you calculate the concentration or molar in the strongly cabinet. Okay. Anyway, let me erase all this thing. Or, you can see that this is a basic proportion to this one because this is essentially constant. It's not going to change. Okay. Then we have 2f times mu Austin weakness. Okay. So we can also write sigma p, basically sigma holes. Just write sigma holes. Basically proportional to, I just leave this out, then times mu holes. Right, sigma electrons proportional to the number of electrons with the mobility. Of course, this is basically the ionic conductivity. The electronic conductivity is basically this plus this one here. Okay, understood. All right, so let's translate this to this one. But before we do that, so you need to know that this guy is much smaller than this two. Okay, so this two are much larger than the mobility of Austin weakness. This is kind of understandable because the electron and the hole, they move much faster than ions, right? That's why at room temperature you can never have a measurable Austin ion conductivity in the Stirling catalyst. You have to go to something like 500, 600 degrees C, okay, to measure that. Okay, so although the concentration of this one is very high, okay, however, if you think about the conductivity, you have to time this one, which is very low. Okay, so this thing is actually down here. It's not concentration anymore. It's sigma. Okay. You can go ahead to convert this to. Okay, so the whole concentration is basically something like, let's see, let me erase this a little bit. Let me erase it a little bit. Okay, so this is the sigma hole. Okay. So the same thing you can do to the sigma electron. Okay. Okay. So of course, when you measure electronic conductivity, we will measure this one. So this is the summation of these two, right? So if you plot that one, remember this is log sigma, okay? So which means that it could be 10 to the minus 3 here, could be 10 to the minus 5 here, right? So which means that the electronic conductivity will follow the one with higher conductivity. Will basically follow this one. So this is your electronic conductivity. Okay. So this basically gives us a very nice way of quantifying the defect concentration, right? So because now we know that if we measure, so if we say we take a piece of strongly carbonate and we kind of put the 2 electrodes, so these are electrons, and then we measure the conductivity by changing the Q2. So let's imagine we put it into this one, then put it into a strong environment, and then we change the Q2. So what we can measure is basically points like this. Okay. For the high Q2 regime, we have really p-type semiconductors with the slope of 1/4, right? For the other regime, we have 1 over -1/4. Okay. So basically, experimentally, it's really something like this. Okay. And another thing is like if we can measure the lowest point. Okay. So for example, if we can measure something like this one. So this is, again, this point is special. So this point, we have, this one is equal to that one. Electron and the hole concentration, they are the same, right? So they are basically square root of this one. And then here, the electronic conductivity should be square root of KEL. This proportional square root KEL times electron mobility plus hole mobility. Okay. For a minute, we'll know why that's important. Okay. So, however, if we measure the total conductivity, so if we measure the total conductivity of both ionic and electronic conductivity, so what we get? So what we get is kind of everything we see. Okay. So for most cases, because the mobility of electrons is much higher than ions, we follow the trace of electronic conductivity. Only here, when both electron and the hole they are sufficiently low in concentration, this guy, the ionic conductivity actually takes place. So in reality, when you go down here, so you kind of see many data points here, which is a little bit above what you expected. Okay, so basically when you do your experiment, when you measure the conductivity as a function of Q2, you get a function of the data point here. So again, so this is in the log plot. Okay. So then you can say, okay, I connected both, then it's 1/4. Okay. Then you measure some more data points here. Okay, then you say, okay, I find that it's 1/4. However, in the middle, you imagine you're going to follow this. However, it's actually not. So it's usually something like this. Higher than expected. So essentially, this part is basically where you have the ionic conductivity. Okay. So this is basically this part here. Okay. Okay, so I guess the last thing we're going to talk about is that, so usually when you do experiments, you can either change the Q2, or another very convenient way is you change the temperature, okay, to measure it. So let's think for a minute. If you take the same sample and you start changing the temperature, what happens? Okay. So if you change the temperature, so what you have is you again go somewhere over here. Okay. So remember that. So this is the chemical Riemann constant for this chemical reaction here. Basically, form the Austin vacancy. Okay. So this will be some kind of exponential minus delta H let's just write out H because you can ignore the entropic term. Oh, actually, because it can cost energy, right? Which means that if I increase temperature, so usually this thing increases, right? Because this part becomes smaller, right? So which means that if I increase the temperature, I'm going to increase this one, okay? So however, this is still fixed. So the only way means that, so this thing will increase. Okay, so the concentration of electron will increase. Okay, of course, if you go here, you also increase the hole concentration. So end of the day, you still have 104, but when you look at here, you actually change it to a different, let's say. So this is at a higher temperature. Okay. So basically, you have a new chemical equilibrium at higher temperature. So again, so this is the electron, so this is the hole. Okay. So if you go over here, so what you have is that, okay, so the thing is going to change. First, the temperature is going to affect the mobility of Austin vacancies. So we're going to discuss why that's the case in the next week. But if you go to the high temperature, so this thing is going to increase, then usually exponentially. Okay, so which means this thing will go in here. Okay, so this is higher T. Okay. For the electron as a whole, so if you increase the temperature, the mobility actually drops. Okay. So let's say, but the temperature dependence is much less sensitive than the mobility of Austin vacancies. Okay, let's say they are roughly the same. However, the concentration does change. Okay, the concentration basically, you can see this point, it shifts to the other side. Okay, so basically what you have is you have here, basically you have something like this. Okay. So anyway, so if you measure it, let me just draw it here. So basically at low temperature, so what you measure, is something like this, because you have Qiyang conductivity here, N type, and you have ionic in the middle. Okay. And if you raise the temperature, so you're going to change, you basically change the, again, you have 1/4, the slope is not going to change. And you have more ionic conductivity. And if you draw the line here, so basically this point is going to change. Okay. So I guess, so what I'm going to do is that in the homework, I'll give you a question about strontium titanate to solve for this. And there you will see that you can have the literature value and you will see what this is really about. However, so let me just quickly summarize what we discussed. Okay, so essentially, so it basically gives you another way of knowing the Broward diagram. So essentially, you'll see that this power law, -1/4. So this power law, they are actually like a fingerprint for what kind of defect chemical reaction you have. For example, you see, you can summarize kind of the principles. So basically, you have defect concentration as, for example, the PO2 over the N. Then the N is actually like a fingerprint. Right, so if the n is positive, so that usually means that you have the, for example, holes, right? For example, here, all the holes or the p-type connectivity, n is positive. Okay. Of course, that can be 1/4, 1/6, depending on the specific p-type chemical reaction. And also, if you have other geometry, not just 1 to 2, the things will be more complicated. Of course, you can have this smaller than this one, that should be the electrons. Okay. So another thing is if you measure conductivity, sigma as function of log Q2. So that actually gave you a way to reconstruct the Broward diagram. Or at least to know something about defect concentration. Right, so if I measure conductivity, I see that, okay, so it's 1/4, I can kind of guess that it's dominated by holes rather than electrons. Okay. So it basically has something to do with defect concentration. Okay. And so the third thing is the temperature. So if you change the temperature, so you should think of the temperature will change the KO, KEL, maybe KF, because these are some kind of exponential. You can write delta H or whatever, thermodynamic quantity of YT. If you change the temperature, you can change that. Okay. So then you're going to change the Broward diagram. Okay. So I guess today we basically talk about two things. First, you can understand the Broward diagram. And if you know that for something like lithium containing compound, it can help you to understand any storage. Okay. The second thing is the way to understand the conductivity, right? So if you measure the conductivity, you can also know something about the Broward diagram, defect chemical equilibrium. Okay, so next we are going to really talk about the detail about the conduction of ions or diffusion.